right, I'm going to scroll up on that screen over there. Yep. All right. Quick recap. Quick recap. A couple things to be careful of as we talk about polygons. 1, 2, 3, 4. This is a quadrilateral, right? Not what you'd imagine. Probably if I said picture a four-sided polygon, probably not the first one you would imagine. However, it still has four sides. What is the sum of the interior angle measures of any quadrilateral? 360. Very good. So these angles, 1, 2, 3, 4, add up to 360. Can I find each one of them by taking 360 and dividing by 4? No, because they're not all equal, right? They're not all equal. I'd have to be told more information. So in general, the sum of the interior angle measures is, for any polygon, what's the formula? N times 180. N minus 2 times 180. And what they were trying to get you to see in the picture was, isn't there 180 degrees in each triangle? And what they said was they called this vertex A. And if you draw in a diagonal, do you see triangle 1 and triangle 2? Two triangles make up that quadrilateral. 2 180s. Well, where did the 2 come from? Well, 4 minus 2 is 2 times 180. And then they tried to get you to see that if you had a pentagon and you take a vertex and draw it two non-consecutive vertices. Consecutive means next to each other. So that would be consecutive, that would be consecutive. You can only draw on two unique diagonals, right? Now there's 1, 2, 3 180s. The 3 comes from 5 minus 2 times 180. That's for the sum of the interior angle measures. Now, if it says sum of the interior angles of a regular hexagon, then if you found the sum, you could divide by 6 because it's a regular hexagon. Now, outside angles, exterior angles, this is just a quick review, by the way, because we're going to move on today. Exterior angles always add up to 360. So as you draw these fins that come off this pentagon, this angle plus this angle plus this angle plus this angle plus this angle add up to 360. If my arm doesn't dislocate, I can show you. All right. So if you put your elbow here and go that way, and then go up to here and go that much farther, and then up here, that much farther, and then down here, you see I went in a full circle, right? If you go incrementally all the way around, you'll see it goes in a full circle, a full 360. All right. Questions on the homework? Any questions on the homework? All right. Today, we're kind of skipping around. We're going to chapter 11, areas of polygons. What are you talking about? All right. All right, I will not be here tomorrow. I have I'm helping out with the sectional tennis tournament this all day. I will not be here. So instead of doing a lesson, we're going to do a lesson today, worksheet tomorrow. Sorry, we're going to do it in reverse. We're actually doing the lesson today, and then you guys have a kind of a worksheet. That's more like Friday's stuff than it is like today's stuff. But instead of having you do a brand new lesson without me here, I'd prefer you guys are here with me to ask questions if you have them. So while you guys are getting that, a quick glance at the week ahead. Worksheet tomorrow, review on Wednesday, quiz Thursday. Quiz on Thursday, angles of polygons and area. Friday, by trig project. It's not really a project, it's more like an activity, but it's going to be summative points. That's where we're gonna download an app on our phones to do angles of elevation. You take your phone, you go with a partner, and you look up at something. It'll be a guided activity. We'll walk around to flagpoles and goalposts and stuff like that. Record the angle of elevation from your phone. You'll have someone look next to you, and then do a quick SOHCAHTOA calculation and find out how tall objects are. We'll have to figure out how far we are away from these objects with some tape measures. So we start that Friday. Later in the week, I'll remind you if you could bring in a. Well, we won't need a ton of tape measures, but I'll try to have a couple of volunteers bring in some tape measures, and it'll make our activity go quicker. We'll do that Friday and Monday, and then we'll get into exam review. Crazy.
So we have an actual exam.
You have an actual exam. All right. Quick glance at a rhombus and a kite. All right. Do you know what a kite is, other than the actual thing you fly? How many sides? 4 sides. Why is it not a parallelogram?
The sides are parallel. The opposite sides are parallel. It's
Hey guys, gentlemen, you should listen. Yeah, like a rhombus, the opposite sides are parallel, right? Remember, parallelograms, we had rectangles, rhombuses, squares. Kite is not in that family of parallelograms. How would you describe a kite to someone? Even if you don't know before right now, how would you look at the sides and describe it to someone? Paige?
adjacent sides are congruent.
Good. All of them?
No.
You're right. We just need to add a couple little words. This is how we start a definition. We start off, we're like, well, I might need to adjust that a little bit. I like it. You're right. 2 pairs of adjacent sides are congruent, right? Now, that doesn't mean all of the pairs of adjacent sides are congruent. I know what Paige meant. 2 pairs of I'm kind of being mean today. All right, 2 pairs of adjacent sides are congruent, right? So here's the interesting thing about a kite. Those opposite sides are not always going to be parallel. Most of the time they're not. All right, it's possible that you have 2 sets of adjacent sides that are congruent. Yeah, we do right here. But that's not the requirement. One might say exactly 2 pairs of adjacent sides are congruent, all right, for it to be a kite. Now, do you see what we're calling the diagonals here? This is diagonal 1. This is diagonal 2. Okay, the diagonal of a polygon. It's those diagonals I drew in on the first slide to show you how many 180s there are. Okay, diagonals connect non-consecutive vertices. So in a quadrilateral, there's 2 unique diagonals. All right, and the area formula for these is 1/2 d1 times d2. 1/2 d1 times d2. All right, what is your first blank? Ooh, we're skipping some here, aren't we? I'm getting ahead of myself. Do you guys have this one in your guided notes? You just stick to the scripts. One, 3. So what's your first one? You guys have this one? Let's try.
No.
I think we're gonna draw in area of, to find the area of a regular n-gon. There we go. Is this your first one in that box? Not the fill in the blanks. We'll get back to that in a second. The box though?
Yeah.
Okay. So we have these things called. That's not the one in the box.
No, that one says isosceles triangles.
To find the area of a regular n-gon with side length s and a polygon p. All right, we'll go back. You guys will need to know a couple key terms, and I might have not put these in the correct order here. All right, so we don't know this word, apothegm. It's kind of a funny word to say, all right? Apothegm. So we have what's called an apothegm. We have what's called well, not a radius. I mean, do you see how that circle's drawn around that hexagon there? A hexagon does not have a radius. Do you agree with that? Like, what's a radius of a circle? It's a segment that's the same distance to the outside of the circle at all places. Do you agree if I were to draw in this green segment, just picture the hexagon here, okay? Just ignore the circle for a second. This distance here is different than this distance here. Do you all agree with that? We'll do it again. The distance from the center to this vertex is different than the distance from the center to the side of the hexagon. How would you argue that with someone without using a circle? How would you argue that the distance from the center to M is different than the distance from the center to the sideline? The perpendicular distance there. What's that?
It's farther out.
Farther? But why? Someone's going to be like, I disagree. Why?
Is the apothem the distance from the center to the side? Or is that not?
Yeah, it's that purple one I drew in that's perpendicular to that side.
So should we write that down?
We will in a second.
Okay.
Use a triangle argument. Do you guys see this isosceles triangle here? Yeah. No. In that small right triangle, isn't the distance from the center to M the hypotenuse, and isn't the distance from the center to the side a leg of that right triangle? They have to be different, right? So when you go to draw in segments within hexagons, you have to be careful. Okay? This new term for us is called an apothem. And it's from the center, it's the perpendicular distance to the side. It's the perpendicular distance to the side. All right? That's the apothem. Is that one of your filaments? The apothem is the distance from the center to a side. And I would put perpendicular distance if I were you. Now, what do you guys think we would fill in there? The blank is equidistant to the vertices. Well, what are the vertices on? Like, if I draw that circle around it, what are the vertices, the distance from the center to the vertices called?
Radius?
A radius, right? Now, it's only a radius if you have a circle around it. So in this context, we could put, the radius is equidistant from the vertices, or the center is equidistant from the vertices. But that's only in the context of building this idea of what an apothem is. All right, so all of these distances from the center to a vertex, this is going to be our foundation of finding this area of this hexagon. Those are all segments that create a bunch of isosceles triangles. Do you see all the isosceles triangles? Okay. Why are they all isosceles? Well, they're all the radius of that bigger circle. So how many isosceles triangles do you see? Ignore this apothem for a second. That would be drawn in a little bit later. 6, right? Now, what about an octagon? 8. Do you know your shapes' names? How about a 10-sided polygon? Decagon, decade, right? 10 years, decade. Pentagon? 5 sides, good. All right. And so angle MPN, this is called the central angle. And again, you have to ignore that right angle's there. So this central angle is pretty easy to find. What do you think that blue central angle is? Any ideas on how we're going to calculate it? Not just for a hexagon, for any regular. 360 divided by 6 in this case. Octagon 360 divided by 8. It takes 6 of these angles to go full circle. 360 divided by 6 in this case. All right. 360 divided by 6 gives us a 60-degree central angle. Now, we're building up to this apothem. All right, I'm going to erase this stuff here for a second, just so we're not confused by what we're looking at. Do you see the apothem? It's not the distance to the vertex, it's the distance to the side. If we know this big angle is 60, doesn't that make each of these 30? Right? And so, how are we going to find out what this blue apothem is? Well, it depends on whether they give you the length from P to N, or they give you the side length of the hexagon. What if they give you the side length of the hexagon? Wouldn't you cut it in half? Like say this whole side is 8. Wouldn't this part be 4? Because when you cut that isosceles triangle in half, you bisect the opposite side. Okay? If that's 4, make me proud, what's the apothem? Make me proud. Make me proud. You know this. That's right, 4 thingy 3. 4 radical 3. Emma, that was impressive. 4 radical 3. Oh yeah, this is a 30, 60, 90 special right triangle. It all comes, Emma, full circle. Very good. Very good. So 30, 60, 90, we have 4 radical 3. We don't need it, but what's the hypotenuse here? 8. Very good. Very good. Very good. Now, how are we going to find the area of the hexagon? Well, couldn't we, 2 options here, okay? Couldn't we find the area of this isosceles triangle and multiply it by 6? Okay. Well, what's the area of a triangle? 1/2 times the base times the height. Does anybody have trouble remembering that formula? Be honest with me. We're good? Okay. You know base times height's a rectangle. Slice it diagonally. Half of that, right? Half of the base times the height. Half of a rectangle. So what's the area of this yellow triangle? Well, what's that triangle's base? 8. What's its height? 4 radical 3. Area of that triangle is 1/2 times 8 times 4 radical 3. Do you agree when you guys are still kind of creeped out by radical, like operations with radicals. Okay, I can tell. Do you agree when you multiply in any order? Right? And I've done this before. But what's like 2 times 3x times y? 6xy, right? 6xy. So what's half times 8 times 4 radical 3? Couldn't I do half of 8 first? And then simplify that and then multiply times 4 radical 3. Isn't it 16 radical 3? 16 radical 3 is the area of one of these triangles. Okay, well, what's the area of the hexagon? There's 6 of those. 96 radical 3. 60. 16 times 6. Right? 16 radical 3 times 6. 16 times 6 is 96 times radical 3. Yeah? Yeah. Is the area of the whole hexagon. Okay. Well, it'd be nice if we had a formula for this, wouldn't it?
Yes, it would be great.
So here is our formula. There's 2 ways to do it. 1/2 times the apothem. So these are the little notes that you have. The apothem is A, so this is the apothem. P is the perimeter. Perimeter of what? Well, the whole shape. Or 1/2 the apothem times n times s. What's n? The number of sides, and s is the side length. Well, what happens when you take the number of sides times the side length? You get the... What if it has 4 sides and each side is 3? Isn't that giving you the perimeter anyway? Like, isn't n times s just the perimeter? I think we missed one fill in the blank, didn't we?
Yes.
Bottom one.
Yes.
It's a central angle. Central angle of a regular polygon. And then the last blank there. How do we find that central angle? Remember talking about that? Take 360 divided by, well, it was 6 for that one, but in general, 360 divided by n. Very good, the number of sides. And that's just to find the central angle. 360 divided by n. N is the number of sides. Anybody need that repeated?
Yes.
Which part?
The last one.
360 divided by n. So quick example, then we'll go do the actual examples out there just to practice finding these. What if it has 8 sides? I'm a visual person. I like to draw these in. You don't have to do it every time. It's a good habit to do it early on. The first thing you would do is you would draw in that, and then you would draw in your, what's that called again? What's the dotted line called again? I heard someone say it. Apothem. It sounds like you're saying it wrong. Apothem. That's the apothem. But if you draw in one of these isosceles triangles, isn't it that angle that's the central angle? This one would be 360 divided by, how many sides are there? 8. What's 360 divided by 8? Here, 45. Here's a great. Yes? But if we draw on that apothem, doesn't that apothem cut 45 in half? So we just have to be careful with these. So let's do an example that's on your guided notes, I believe, right? Practicing finding these. Not on your guided notes? I'm falling apart. All right. You don't need to write this down then. What's angle AFB?
Central angle.
It's a central angle. How do we find its measure? 360 divided by 5. Good. What's 360 divided by 5? Is that 72? 72 degrees is that one. Right. How would we find AFG? AFG, this angle.
It's
Half of it. 36. How about GAF? GAF.
36 plus 30 minus 54.
What'd you say?
54.
Yeah, aren't they complementary? Isn't this a right triangle? Aren't these two angles complementary? So if we found 36 there, this one's got to be 54.
Can't you just do 90 plus 36?
The triangle sum theorem?
Yeah.
You can.
Okay.
Yeah. It's called a corollary. It's a shortcut for right triangles. The two acute angles always have to be complementary. All right. Here we go. First example. I hope this is in your guided notes.
It's not. Our first one is a regular hexagon with a side length of 2 feet.
This
And we
is
don't have a
unfortunate.
picture. It really is.
That's
Why?
also not on there.
You just.
Did you print the wrong paper?
Maybe. All right. Regular hexagon with side length
2 feet.
2 feet. All right. Use your hexagon tool. Go ahead and draw this.
Yeah.
You don't have a hexagon tool?
Are we drawing?
Maybe next year. I would.
We get a hexagon tool next year?
Hexagons.
Oh, that was really bad.
This is bad.
6 sides. That was nice, Anthony.
No,
That was
awful. That's awful.
All right, let's do this together. All right, if the side length is 2, the first step you should do, draw in some segments that go from the center to each vertex. Not all of them. Not all of them. And we're going to see a shortcut eventually where we don't necessarily have to draw the hexagon, because once it gets to a nonagon, you're like, I don't want to draw that. Well, you guys complain about hexagons, so yeah. You won't need to draw them. You'll just have to draw one of the isosceles triangles that makes it up. Does that make sense?
Yeah.
So here we go. If this is our hexagon, we always want to do a couple things. One, draw in the apothem. Sometimes you're given the apothem instead of the side length. So what is our central angle? 360 divided by 6, which is 60. Now be careful. These are 60. But when we go to find the apothem, we need to cut it in half because we have 2 right triangles, each of them being 30 degrees at the top. Next thing we have to be careful of. Because we're finding the apothem and we want to use that right triangle, we're not going to use the 2. We're going to have to cut that in half and say this side is 1 and this side is 1 if the whole side length is going to be 2. Now, the area formula I like to use most times is 1/2 times the apothem times the perimeter. Do we have the perimeter? Well, not yet, but it's really easy to find. What's the perimeter of this hexagon? 12. It's got 6 sides. Every one of them is 2. 12. We have to find the apothem. All right. Now, this is an easy one. Hexagons are easy. All right. They make 30, 60, 90s. We have those memorized. Easy. If this side is 1, what's the apothem?
1 right
1 radical 3.
I don't know which one is times
The other side.
From short to hypotenuse would be times 2. We don't care about this length, do we? It's helpful to draw it in, but we don't actually need that length. We want the apothem. The apothem is 1 radical 3, or just radical 3. Now, what if you forget? What if, hypothetically, special right triangles left your mind the moment after you took the quiz? Maybe even before. Do you agree we could use SOHCAHTOA?
Yeah.
Watch. 30-degree angle. Isn't 1 the opposite? Isn't A the adjacent? A is not standing for adjacent here. It's for apothem, but how convenient. Isn't it opposite, adjacent? I would use tangent, wouldn't I? The tangent of 30 equals, what's the adjacent? What's the adjacent side? Nope. What's the opposite side from 30?
1.
Over, what's the adjacent side? A. How do I solve? Multiply and then divide by tangent of 30. Right? Go ahead, type it in. What do you get? 1.7.
1.73.
1.73? McKenna. No, I would not. I would not take 1.73. Now type in radical 3 for me. It's the same. It's it's magical.
Thanks, Paige.
Now it's time for the area. 1/2 times radical 3 times 12. Well, it's 6 radical 3, but we could also take decimals here. 6 radical 3. Come on. Come on.
Wow.
Or
I can get it's the R.
10 point, what is it?
10.39.
39. 10.39. That's a 10, and that's a 0.39. Awesome.
Wow.
Wait, so we're not figuring. Isn't it 36 radical 3?
What?
It's 6 radical 3.
Yeah, but then you multiply by 6.
Yeah, are we finding it of the whole?
Yeah, it says a regular. Find the area. The whole thing.
When we did half the apothem times the perimeter, that's the area of the whole hexagon.
Oh.
I gave you the option of doing 6 separate triangles. If you want to do it that way, here's what you would do. Ready? Let's just do an area of one of the isosceles triangles. Okay, area of the triangle. 1/2 times, what's the base of that triangle? 2 times the apothem, right? Radical 3. Isn't the area of one of those just radical 3? How many of those triangles are there? 6 radical 3s. Okay, so when we built up the formula, we did half the base times the height, but we're like, wait a minute, if there's 6 of those, we could just replace the 6 triangles with that perimeter as all of the bases added up. Okay, this is your eyes up here, because I think you guys missed this. This is the area of the whole polygon formula. Not just one of the triangles. That'd be half the base times the height. The area of the whole polygon. 1/2 the apothem times the perimeter. All right. What's your next one? I'll do whatever you guys have. Pentagon. Pentagon with side length of 16. Now, I'm going to give you an option. What if you are just wanting to draw a triangle? Here's the apothem. Wouldn't you put the 16 here? And you know there would be 5 of these triangles to make up that pentagon, okay? Because if I say of a 14-gon, you're not going to draw a 14-sided polygon.
No.
Okay? You're going to draw one triangle of the 14th. And you're going to use that to show your work. Does this make sense to you?
Yes.
Do you need me to say it again? Okay. So here is the pentagon. Here is the blown up version of that triangle. Okay. Well, what's our formula for the area of a pentagon? 1/2 times apothem times the perimeter. Well, good news. I already have the perimeter. It's 5 sides, 16 each. Isn't that 80?
Yeah.
Isn't the perimeter 80? So we just need to find the apothem. Well, how do I find this angle? This central angle. 360 divided by
65.
360 divided by 5. I believe that's 72.
Yeah.
That's 72, but to find the apothem, we're going to split that in half with 2 36s. 2 36s. Is everybody with me? This is why that triangle is very helpful for you to draw. It will help you stay away from making a simple mistake of forgetting to cut it in half. A lot of people are going to use that 72-degree angle, but you have to cut that in half. What else do you have to cut in half? The 16 to get the sides of 8 and 8. Can I use a special right triangle here? No, it's not special. Okay, please don't tell it that. It's not special. So McKenna, we have to use SOHCAHTOA here. We have to. So if I want to find the apothem, well, wait a minute. I'm still using tangent, aren't I? Opposite adjacent. Tangent of 36 equals blank over blank. What goes up top? The 8 or the A? The 8? Is it 8 over A or A over 8? I'm using SOHCAHTOA.
8 over 8.
Tangent of something equals opposite over adjacent. Opposite over adjacent. Is it 8 over A or A over 8? 8 over A. Opposite from 36 is 8. The adjacent is A. So multiply the A over, divide by tangent of 36. 8 divided by the tangent of 36 is?
11.
Did you say 11.01?
Yeah.
I agree. A, apothem, is 11.0. Come on. 1. We plug that into our formula. Area is half times 11.01 times 80. I'll be honest, I save some time. I just take half of 80 first. I take 40 times 11.01. I get 440.44. 440.44. Did yours have a unit of measure? Centimeters squared, right? So it'd be centimeters squared. Centimeters squared would be the unit. Does this make sense? The only tricky part, are you ready? What if they give you a picture? Eyes up here. What if they give you a picture and they say the distance from the center to the vertex is 12? Paige.
I'm just confused. So I did 8 radical 3. Is that correct for the apothem?
It's not a special right triangle. It's not a 30, 60, 90.
I did the same thing.
All right, you guys see how this is 12? Here's what you would have to do. You'd have to find this side first using opposite and hypotenuse, sine, and then the apothem using adjacent and hypotenuse. You'd have to do 2 SOHCAHTOAs to do that one. Make sense? Homework.
Open it up.
All right. There's actually not that many area problems here. A lot of them are just find the angle, find the side length, find the whatever. So these are all good. Make sure you write this down. There's homework. There's homework, Levi. Homework. There's homework.